Okay, so we are interested in discovering what happens to the graph of f of x is x squared when we look at the graph of x squared minus 4 and then a little bit after x squared plus 4. So to do that, we need to start with just what does f of x equals x squared look like? Um, Hopefully you're at a place where you can just recognize this, but if not, that's okay. But you do want to get to that place where we say f of x squared and you know exactly what it looks like. So if we were to graph x and f of x, um, typical values we plug into x squared are -2, -1, 0, 1, and 2, even though its domain is all real numbers and I can technically plug in whatever I want. These give me a pretty good idea of what the graph looks like. Um, and if we were to simplify that, we would get -2 squared, which is 4. Make sure those parentheses are there so you get a +4. -1 squared, which is 1. Same thing. Make sure the parentheses are there so you get a +1. 0 squared, which is 0. 1 squared, which is 1. And 2 squared, which is also 4. So if we were to graph this, even though I have my table here, I am going to make sure this is labeled. It is very important that your graphs are always labeled and as neatly drawn as possible. Think about the quality of your graph as honestly part of your solution, right? You're wanting to create something that looks really good. Okay, so we're going to line up our points. I have -2, so 1, oops, let's make that a little more exact. 1, 2, -1, and 1, 2, 3, 4. So we have a point here. We have a point at -1, 1, so we have a point here. At 0, 0, we don't necessarily have to label the origin, especially when we have other points labeled, but you can if you would like. And I'm going to zoom in a little bit here. I hope. There we go. And then we have a point at 1, 1, so back here, and 2, 4. Now, this graph does extend on forever, right, towards infinity in both directions. I don't need to graph all those points, but this does give me a pretty good idea of what this graph looks like. It's a little shaky. I'm going to try to clean it up. There we go. Okay. Again, it should be pretty smooth. You should be able to draw it without picking up your pencil, pen, whatever whatever you're drawing with, and it should have that kind of smooth, curved look as much as possible. It should not be mistaken for an absolute value function, right? Those should be pretty clear between the two, which one's which. Okay, so our first question is what happens to this original, we're going to call this the parent function, right? This f of x is x squared. And I guess I could write that there. When we subtract 4. So let's find out. If I have x and I have f of x is x squared minus 4, and I realize this should be g. What do we have? I'm going to start with the same numbers, the -2, -1, 0, 1, 2, and see if it gives me enough of a picture. A lot of times with these parabolas, it helps to have the vertex point, which back here was at 0, 0, and then have these kind of very evenly spaced numbers. That's why we use these. So I'm going to see if that still helps. If not, I'll add some more points. So we can always add more. -2, -1, 0, 1, 2. So we've got -2 squared minus 4. Well, that's 4 minus 4, which is 0. Well, that's different, right? Okay, so now let's see what else we get. Again, -1 squared minus 4 is 1 minus 4, which is -3. Okay. 0 squared minus 4. Well, that's just 0 minus 4, right? So -4. Getting a lot more negatives than we got before, right? Let's see what else we've got. 1 squared minus 4, which is 1 minus 4. We've seen that one before already, right? That's going to be -3. So at least some of that similarities, at least some of those are still there. That's helpful. And 2 squared minus 4, 4 minus 4 equals 0. I'm going to plot these, and if it's okay with you, I'm going to plot them on the same graph. Let me see if this will let me copy. Nope, maybe not. That's okay. I'm going to plot this on the same graph just so we can kind of visualize what's happening. So this point, -2, 0, sits here. So you can already see we've dropped down from the previous graph. Hopefully you can see that well enough. -1, -3. Well, I don't have that labeled yet. So 1, oops. 1, 2, 3. There's -3. So there's a point there. 0 and -4. There's -4. So there's a point there. 1 and -3. And back to 2, 0. Well, helpfully enough, right? I still have my basic shape, right? I still have this parabola shape. So if I were to connect these points, I still have a parabola, but what happened to it? That's the big question. And that's what we want to explore on this page is what's the difference in going from this parent function to this, we're going to call it broadly, we call this a transformation. And it just means that the original parent function has changed in some way. So the specific of the transformation, like exactly what happened to it, in our case is called a shift. So shifts are a form of transformations, but not really. Transformations are not a form of shift. So transformation is kind of the larger definition group. Shift is an example within that group. We did have one more piece on here is what happens if we look at the graph of x squared plus 4. I'm going to just underline this in blue so we know what function that was. I'm going to do that over here on the left. So the only difference here is addition instead of subtraction. So you might actually pause and make a prediction on what could happen here, right? When we subtracted, what happened to all of our function values. And then now we're going to add, and you might be able to predict what's going to happen, but again, in reference to the original, I'm going to stick with the same values and see what happens. Let's see, we've got -2, -1, 0, 1, 2. So we've got -2 squared plus 4. Well, that's 4 plus 4. That's 8. We've got -1 squared plus 4 plus. So that's 1 plus 4, which is 5. 0 squared plus 4 is 0 plus 4, which is just 4. And then we've got 1 squared plus 4. 1 plus 4 takes us to 5 again, right? Again, we see some of these patterns in our answers, our output y values, which is really great, or function values. And then 2 squared plus 4. 4 plus 4 is 8. Okay. So if we were to graph this, I know it gets a little squishy, but we're going to graph this in the same place because I want us to compare the 3. So maybe if I zoom in, doesn't become quite as cluttered. So we're looking at -2, which again, I have that on the x-axis. What I don't have yet is +8. So 4, we have 5, 6, 7, and 8. So I'm going to have a point here. Okay. -1 and 5. There's 5. So -1, 5 is here. 0, 4, 1, 5, and +2, 8. So again, I know my basic shape has not changed. I still have my parabola facing and kind of opening in the same direction. We'll talk about reflections in a little bit. Nothing else has changed except for its kind of location, which it is pretty significant. Let me redraw that. So what we have here, when I compare these three, again, I have my original parent graph, f of x, right? And that just started wherever it normally started. And we're working with x squared, so the story would be the same if you had x cubed, square root, any of our other functions, Michael Phelps swimming, John Travolta dancing, whatever variation, right? But what happened when we subtracted 4, and I want to be clear about how this is happening. This is subtracting 4 after the original function. So this is essentially f of x minus 4. And the result was, compared to this example, was everything shifted down. That's the word we're going to be using here. Shifted down 4 units. And I want us to pay attention to the location. Again, there's a difference. We'll see this a little bit in our examples, but there's a difference between x squared minus 4 versus, let me fully change color here. Let's go with this like pink color. So it's very different versus x minus 4 squared. We will talk about that later, but those two are not the same, not equal. And then what's the difference between, again, our original, our parent function, and when we add 4? So again, this is an f of x plus 4, because this is just f of x as it is. So in this case, you can see from the black to the green, everybody moved up 4 spaces. So we're going to call that shifting up, shift up 4. You could say 4 units or, 4 marks, and it's not the best way to say it. 4 units is usually the best way to go. So we're not officially defining it here. I just want to give you kind of an idea of what it looks like. I do think that this exploration piece works really well if you kind of have time to sit and just play with it. What happens if can take you in a lot of directions, and that's kind of how math is meant to be explored is, well, what happens if I do this? And then you just try it. So that would be some of my recommendation. If you see a question like this on your homework, what happens to this graph if I do this? You don't always have to know that off the top of your head. Sometimes you can do an exploration like this and you just try it and see what happens. So that'd be my recommendation. And that's all I have for you now.